if it ever becomes possible to travel back in time, it may happen because one man asked the right question. In the early 1980s, the astronomer Carl Sagan was writing a science fiction novel about Earth's first contact with aliens. Unexpectedly, it sparked a scientific investigation of time travel.
In Contact, the heroine, Eleanor Arroway, who was a radio astronomer engaged in the search for radio signals from extraterrestrial intelligence. Well, she receives a signal. And the signal, after much decoding, turns out to be a machine. And the machine is a means of traveling great distances.
Inside the machine, a space traveler would sit in what looked like an ordinary armchair. In the movie of Contact, the chair went high-tech, but the idea was the same. A mysterious machine designed by aliens that would transport a human across the universe. But in writing this story, Sagan ran into trouble. Our galaxy is so large that it would take his heroine thousands of years to reach her destination.
That was my problem, to get her to a great distance away from the Earth and the Milky Way galaxy to meet the extraterrestrials and come back and do all that within the lifetime of the people she has left behind.
What Sagan needed was a shortcut through the vast reaches of outer space. And this search would unravel the secrets of time travel.
In the early 1980s, there was a common misunderstanding that you might be able to travel from one place to the other in the galaxy without covering the intervening distance by plunging into a black hole. But there was something about the whole idea that made me nervous. And it was for that reason that I contacted Kip Thorne.
Kip Thorne was an old friend and an expert on black holes.
I was a little upset because he had the heroine in his novel traveling through a black hole, and I knew that you can't go into a black hole and come out somewhere else. The fundamental laws of physics forbid it.
A black hole forms when a large star dies and collapses to a small, infinitely dense point with immense gravitational pull. This warps space so severely that everything nearby is sucked in and destroyed, making travel through a black hole impossible.
If you go down through the horizon of a black hole, at the center you don't find a tunnel that leads you to some other place in the universe. What you find instead is a region where the material of which your body is made, the atoms get stretched and squeezed beyond recognition. And then space and time themselves get stretched and squeezed beyond recognition and destroyed. But if you've gone inside a black hole trying to travel through it, that doesn't matter. You're dead. There was no way you can get through.
I got back a long letter from Kip with about 50 lines of closely reasoned equations, which was a level of detail in response to my phone call that I had not anticipated.
Rather quickly, I recognized that what he probably should do is replace the black hole as a means for rapid interstellar travel with a wormhole. At that time, wormholes were not something that were part of science fiction. They became part of science fiction as a result of this interaction between Carl and me.
Wormholes are like tunnels in the fabric of space and time, predicted by Einstein's equations. Thorne realized they might hold the answer to Sagan's dilemma.
Our universe, it's three-dimensional, but we can pretend it's two-dimensional, so it's like this sheet of paper. And we live in Pasadena over here, and London is over there, and it's thousands of miles from Pasadena to London. This universe is curved up so that through hyperspace, the distance from Pasadena to London is only a few feet. And there is this pipe, this little wormhole, that will lead us from Pasadena to London across that very short distance. And it's like looking through a crystal ball. You see a distorted picture of what is going on at the other mouth of the wormhole, which may be in another galaxy, or it may be near the star of Vega, or it may be in London.
This shortcut was just what Sagan's heroine needed.
I must have gone through a wormhole.
Contact had started something new.
It introduced to the world to science fiction, and also reintroduced to serious scientists the notion of a wormhole as something that was really worthy of thinking about.
With wormholes on center stage, Thorne soon found they had other mysterious properties. They could be used for more than traveling great distances in space. They might also be used for time travel.
If you have a wormhole, then you can turn them into time machines for going backward in time. We thought, how could we have been so stupid? We should have realized that. That's obvious.
What became obvious to Thorne was that time could behave in strange ways inside a wormhole.
Let's suppose that I have a wormhole with one mouth here and the other mouth over there. Now, there are three different possibilities for how time could be hooked up through the interior of that wormhole. The first is that when I stick my arm into this mouth, it came out over there simultaneously. The second possibility is that when I stick my arm into this mouth, it comes out over there only after some delay. And the third possibility is that if I go into this wormhole mouth, then I come out over there before I ever even go in. Let's just see that. It was quite a surprise when I realized that with a single wormhole, you could have time hook up toward the future or toward the past, and that you could actually manipulate the wormhole and change how time hooked up. That was a surprise, but a very satisfying surprise when I really understood how it worked.
Suddenly, time travel seemed feasible, at least in theory.
As a youngster who was fascinated by the possibility of time travel in science fiction, to be in any way involved in the possible actualization of time travel it just brings goosebumps.
A physicist working on the possibility of travel into the past has to be careful not to be labeled a crank or accused of wasting public money on science fiction fantasy.
Doc? Don't say a word.
Stand back! In less than 3 minutes, I shall have escaped this age of madness!
Nevertheless, it is an important question.
Right now, we are in one of those classic, wonderfully evocative moments in science. When we don't know, when there are those on both sides of the debate, and when what is at stake is very mystifying, very profound.
Time is something which at a fundamental level we don't understand.
Newton, of course, thought time was like a river that flowed.
Time is the thing out there that flows, and I go with the flow.
Time is nature's way to keep everything from happening all at once.
It is one of those concepts that is profoundly resistant to simple a definition.
We continue with the sale of Albert Einstein's manuscript for the theory of relativity.
Einstein's theories of relativity are invaluable because they lay the foundations of modern physics, including the possibility of time travel.
Number one of this catalog, and I have a bit of $2 million to start the bidding on this, and $2 million now.
In his theory of special relativity, Einstein declared that time can be altered by speed. The faster you move, the slower time passes.
$3 million at $2,300,000.
In 1971, Joe Haefele and Richard Keating put the theory to the test. They flew 4 atomic clocks around the world to compare the passage of time on an airplane with time on the ground.
I don't trust these professors who get up and scribble in front of blackboards claiming they understand it all, because I've made too many measurements where they don't come up with the numbers they say.
Richard had told me that in all the previous work he had done, he had never seen the effect of time dilatation.
I hadn't.
Had never seen it.
I knew what was being predicted and that, but it always seemed to me that the best proof is to measure it.
Measure? Well, hopefully it's going to be of the order of 1 minute.
To see how time slows down with speed, they had to fly all the way around the world in the original experiment. Today's atomic clocks are more accurate, so the warping of time should be apparent even on an ordinary transatlantic flight.
Champagne for you, sir? Yes, one for me and one for my friend.
Certainly. About 5 minutes past 4 local time, which is 5 minutes past 9 English time.
Einstein said time is that which is indicated by clock. I think I know what a clock is, therefore I think I know what time is.
Seem to be following an unbelievably constant track.
En route, they collected data from the pilot, then put it into Einstein's equations to predict the time change.
We have accumulated so far a change of 34 nanoseconds. Broadly speaking, it seems to confirm the original prediction. The clock will have gained somewhere between 37 and 40 nanoseconds when we land in about half an hour's time.
Suppose you would live for 100 years and you would spend your entire life on one of these aircraft flying around the world. You could expect to be younger than people who did not do that by about 1/10,000th of a second.
The UTC, USNO master clock.
To measure exactly how much time changed relative to time on Earth, the clock on the airplane had been synchronized with the international standard at the start of the trip. Then it was compared to the same standard when it landed in the United States.
If we put other cables in here, that changes by about...
The clock on the plane disagreed with the ones on the ground by 40 billionths of a second, just as Einstein predicted.
At $2,700,000 now. At $2,800,000. At $2,900,000. Here at $2,900,000. At $3 million, $3,100,000, $3,200,000, $3,300,000 is here. Don't wave back there. Fair warning now at $3,300,000.
But taken to an extreme, Einstein's theory that time slows down at high speeds has even stranger consequences.
This is sometimes described as the twin paradox. 2 identical twins, one of whom goes off on a voyage close to the speed of light, the other of whom stays home. When the space-traveling twin returns home, time has dilated for him or her. That is, he or she has aged only a little, while the twin who has remained at home has aged at the regular pace. And here you have 2 identical twins who may be decades apart in age.
Applied to a wormhole, this curious phenomenon might make time travel possible.
There are several different ways to turn a wormhole into a time machine if you are a clever and infinitely advanced civilization. By an infinitely advanced civilization, I mean somebody who can do anything their heart desires, except they can't violate the fundamental laws.
What they could do is take advantage of the twins paradox and send one mouth of a wormhole on a voyage into outer space. As the wormhole mouth approaches the speed of light, time slows down relative to the wormhole mouth that remains on Earth. At the end of its high-speed voyage, the traveling wormhole mouth returns to Earth, where it can be picked up by its owner. Just like the twins' paradox, less time has passed for this mouth of the wormhole than for the other end that stayed behind on Earth. The wormhole is now a tunnel, with each mouth located in a different time.
If I now go into this wormhole mouth today, I will come out of that mouth yesterday.
So in theory, an advanced civilization might turn a wormhole into a time machine. But the practical details are something else again. Where would they find a wormhole in the first place? The answer grew out of the work of Kip Thorne's former teacher.
I like to think of space and time as analogous to the ocean, and changes in it as analogous to waves on the surface of the ocean. But those waves, of course, don't show up when one's miles above the ocean. It looks flat. Then as one gets down closer to the surface, one sees the waves breaking and the foam. I see no way to escape the conclusion that similar foam-like structure is developing in space and time.
Wheeler thinks the space between atoms is filled with bubbles. And this quantum foam, as he calls it, gives rise to incredibly tiny wormholes.
Let's suppose we begin at the size of Britain, and we squeeze ourselves on down smaller and smaller, past the size of a human being, down to the size of an atom, and on down to the size of an atomic nucleus. We're then halfway to the scale of quantum foam. We have to then begin at that scale and go on down. As much as we went from Britain to an atomic nucleus, we have to keep on going down. It's another 20 powers of 10 on down. We get to a minuscule scale, far smaller than anybody has ever been able to reach with experimental apparatus. And there, the fundamental laws seem to tell us there must be quantum foam. Space, as we know it, must cease to exist in this smooth sort of a way and must become something more like a froth of soap suds. This quantum foam we can think of as having bubbles, but we can also think of it as having little handles like the handle on a coffee cup. That is a wormhole. It's something that reaches from over here in the foam to over there.
Thorne speculates that if quantum foam exists, an advanced civilization might be able to grab one of these tiny wormholes and enlarge it. But there's another problem.
We then had to face the fact that the one kind of wormhole that we knew as a solution of Einstein's equations was a wormhole that lives for only a very short time. It has a throat that expands, opens, and shuts in a flash so fast that anybody who tries to travel through it in that flash while it's open can't manage to get through. They get crushed in the pinch-off.
To travel through a wormhole, a human being would have to find a way to hold it open.
So we then ask ourselves, what is it that you need to thread through the wormhole to hold it open long enough for somebody to travel through it? And Einstein's equations told us the answer. We just had to do a page or two of calculation. What you needed was something very exotic, some material that has negative energy.
The bad news is that if you want a wormhole about 1 meter across, which is a really minimal requirement for something to put a human through, you need about -1 Jupiter's worth of this exotic matter.
So the repellent force of a planet-sized amount of exotic matter would be required to hold a wormhole open. But it's not as far-fetched as it might sound. Scientists have found that tiny amounts of such negative energy can be made in the laboratory.
Comes down here and supports this triangle.
All ordinary matter has positive energy, but exotic matter can be produced by squeezing energy out of a vacuum created in a tiny gap between two metal plates.
Now, when you bring two plates close together, photons of long wavelengths can't exist between the plates, so you exclude some of this energy from the system. When you do so, the energy between the plates is lower than the energy outside, and so there's a force between these two plates.
The force actually pulls the plates together, and that's critical because that tells you that the energy density between the plates has to be negative, and that is the key to it actually being exotic matter.
We just did it for fun, and it's built with just junk we found around the lab here. Okay. But in fact, we can measure an extremely tiny force with it.
That experiment, from our point of view, is a proof in principle that at least small amounts of exotic matter, effectively negative energy, do exist in the real world.
If enough negative energy could be collected, time tourists of the future might be able to hold a wormhole open long enough to make a safe journey into the past. Hoping that large amounts of negative energy might be possible, and speculating that wormholes could be extracted and enlarged from the quantum foam, Thorne took the plunge. He published his ideas about time travel in one of the most prestigious physics journals.
My concern was the word time machine in the title, and my worry was that the popular press would see this paper and would start to ballyhoo it in a manner that caused our serious scientific colleagues to pay no attention to it as being crackpot stuff. Very quickly, the rest of the press grabbed hold of it. Here we are, we've invented time travel. There were other stories that basically had us building time machines in our own basements. And I rather quickly pulled back and told the Caltech Public Relations Office, I do not give interviews on this subject. I told my research group's administrative assistant, I do not return telephone calls from the press on this subject. I will talk about anything else but not time travel.
But Thorne's work brought other scientists out into the open.
When I realized that my friend and extremely great scientist Kip Thorne published it, I immediately called him and told, thank you so much for that. Now I will publish, I will work on this subject also.
He was overjoyed. On the other end of the phone, he said, oh, Kip, it's absolutely wonderful. Your paper's wonderful. You've broken the barrier. If you can do research about time travel, then so can I.
Igor Novikov had been working on time travel in secret for years. He was intrigued by the trouble that time travelers might cause if they went back and tried to change history.
Once it appeared that time machines were a real possibility, we then had to face the question of paradoxes, of going back in time and changing history, and thereby causing the foundations of physics to crumble beneath us.
You're in focus now, Paul. Press the button, Harvey. Press the button, my friend. Send me back into time.
Time travel would seem to lead to contradictions if one was able to go back and change the past.
The grandfather paradox is a very simple science fiction-based apparent inconsistency at the very heart of the idea of backwards time travel.
If I have a time machine, then there is the danger that I may go into the time machine, go back in time, kill my grandfather before my mother is conceived so that she can conceive me.
Where does that then leave you?
How do I get here?
Do you instantly pop out of existence because you were never made?
But then you couldn't have gone back, and so on.
Hurtling back through time creates paradoxes that have fueled dozens of Hollywood productions.
Dudes, you guys are gonna go back in time.
Anything you do could have serious repercussions on future events. Do you understand?
This is gonna cost me.
A serious consideration of backwards time travel must confront these paradoxes.
Billiard balls provided us a way to study paradoxes with time travel without getting into the nasty business of free will of human beings.
Billiard balls behave in predictable ways according to the laws of physics. Cause always precedes effect. But what happens if time travel is possible?
If I have a time machine, the story is quite different.
Imagine the pockets of this billiard table are the mouths of a wormhole time machine.
In this case, I have only one billiard ball, and I send that billiard ball into this mouth of the wormhole, and it will then come out of that mouth before it entered this mouth, hit itself and prevent itself from going into the first mouth. Voila, a paradox. It's the billiard ball version of going back in time and changing history.
Of course, this problem was discussed a lot in literature, in movies, in science fictions. But I'm talking not about fantasies, but real science.
Having developed simple versions of the paradox, we then set about trying to figure out how to solve these. How will the laws of physics behave if time machines are permitted? In searching for a resolution of the paradox, we were led by a principle introduced by Igor Novikov, which said that nature will only allow those behaviors that are absolutely self-consistent.
In order to be self-consistent, a ball emerging in the past must knock itself into the time machine so it can come out again along a trajectory that will knock itself back into the pocket. Novikov wrote mathematical equations for the possible outcomes of a ball hitting itself and found that a self-consistent solution always exists. This implied that nature would not allow a paradox to arise.
This is the main principle. All these events must be in self-consistency with each other. It's so simple, so obvious, but more of that. We gave the strict mathematical proof that this principle is the consequence of the basic ideas of the physics.
By the same token, Novikov's findings implied that the laws of physics would prevent a time traveler from rewriting history.
Yes?
I'm here to prepare your room, mein Herr.
What has happened has happened. It cannot be changed. It cannot be repeated twice in different ways.
Human beings aren't billiard balls, and we might like to believe in free will. So a sufficiently stubborn human would seem to be able to get around any sort of consistency condition by just demanding that he does something different.
I can have free will to walk along this wall without special equipment. It's my free will. Can I do that? No, I can't. Why? Because of a law of physics, because of the law of gravity. It's forbidden.
Laws of physics, like gravity, already restrain our free will. Novikov thinks these same laws would restrain the free will of a time traveler bent on changing the past.
Driscoll, open up, please. Immediately. Immediately now.
If time travelers can't change the past themselves, could they alter history by sending a message into the past instead? Einstein's theories of relativity showed that if something could travel faster than the speed of light, it could be viewed as going backwards in time. But relativity also says that's impossible. Yet this man may have taken a step in that direction because he claims to have sent information faster than light.
This signal is split into, by an electronic mirror here, into two parts. So we can compare the signal. One is moving through the air and the other one is moving through the barrier.
In this experiment, Gunter Nimms splits a microwave signal in two. Half goes through the air, traveling at the speed of light, and half is fired into a barrier to block the signal. But that's not what happens.
This is an oscilloscope where you see the signal, and then we can see which one is faster.
The two humps on the screen are not in the same place because the microwaves that went through the barrier got to the detector first, apparently exceeding the speed of light.
Only a very small part comes to the other side. But it comes, and this part comes at a velocity which is much faster than the velocity of light.
So how could the microwaves go faster than light? And what was the role of the barrier? Nimms chalks it up to a strange phenomenon called quantum tunneling. At the subatomic or quantum level, the world is ruled by probability and chance, and the seemingly impossible occurs all the time. For example, when a stream of particles like photons meets a barrier, most bounce off. But a few of them materialize on the far side of the barrier and continue on their way. Nimms detected the particles that appeared and measured how fast they got there.
I'm amused about this. We did this for fun. And when we figured out that it's faster than the velocity of light, we did not think about its importance.
Another expert in quantum tunneling is Raymond Chow. He agrees with at least part of what Nimms has found.
In our experiments, we have measured that a single photon can tunnel across a tunnel barrier at 1.7 times the speed of light.
What bothers Chow is not that random photons seem to go beyond the speed of light, but that Nimms claims he can use tunneling to send information faster than light.
To have a genuine signal, you really have to control the signal. But in quantum mechanical tunneling, it's a completely random process. Fundamentally, we cannot send information with this tunneling particle.
Yeah, some colleagues were claiming that you cannot send information, and then we started to transmit Mozart 40, and this is, for instance, the original tape. That's what we sent at a speed of 4.7 times the velocity of light and a distance of about 14 centimeters. Whether you can recognize Mozart 40 or not.
Despite the randomness and uncertainty of the tunneling process, Mozart seems to have gone through the barrier.
The essential question is, what is a signal, or what constitutes information? Has he really sent a signal in the sense of information faster than the speed of light? This is where Professor Nimms and I part company, because we don't really have a rigorous definition of what is information at the quantum level.
Maybe that this is not information for American colleague, but for a German or a British colleague. I think Mozart 40 has some information in it.
Transmitting Mozart is one thing. Convincing others that you've sent it faster than light is another. And so the debate continues, with neither side budging.
I insist on it that we have and we can transmit signals faster than the velocity of light.
NIMPS has found little support for this claim. And few think this will ever allow information to go backwards in time. Still, the idea that time travel for people might become a reality raises a provocative question.
Time travel might be possible, but if that is the case, why haven't we been overrun by tourists from the future?
This argument I find very dubious. It might be that time travel into the past is possible, but they haven't gotten to our time yet. They're very far in the future, and it's the further back in time you go, the more expensive it is. Then there's a possibility that they're here all right, but we don't see them. They have perfect invisibility cloaks or something. If they're so smart, if they have such highly developed technology, then why not? Then there's the possibility that they're here and we do see them, but we call them something else, UFOs or ghosts or...
I think that if people from the future were going to show themselves, they would do so in a more obvious way. What would be the point of revealing themselves only to cranks and weirdos who wouldn't be believed?
But physics does put a limit on how far into the past a time traveler could go.
Relativity theory says in general that once you've made a time machine, you can never use it to go backward in time before the period when it was made. There's no way I can use it to travel back to the age of the dinosaurs or even back to the time of my own birth, because I didn't make the time machine until recently.
So relativity forbids one of the most beloved scenarios of science fiction from ever happening, because you cannot go back before the point at which the time machine was made.
I don't have to worry about the possibility of my going back and killing my father before I was conceived. What I have to worry about is my grandson going back in time and killing me before he is conceived. That is, there's no possibility of changing our past, but in the future, one can change the future's past.
But there is a loophole that might still make even the most far-fetched scenarios possible. According to quantum theory, uncertainty and chance rule the subatomic world. You can never know the exact position and speed of particles at the same time. Instead, you can only give probabilities for their behavior. In a huge extrapolation, some people think that all these probabilities are occurring simultaneously. Anything that might happen actually is happening.
Quantum mechanics is a theory of many parallel universes. Some of them are alike, and some of them are very unlike. There are nearby universes that differ from this one only in the position of one photon or one electron. There are other more distant universes where we're not filming here at all, and there are others where I was never even born.
This is a radical interpretation of quantum mechanics. But David Deutsch finds the evidence he needs for parallel universes in a well-known physics experiment.
I first saw this experiment demonstrated when I was an undergraduate. In fact, it's a very old experiment. It was first done in 1909.
This is our light source for the experiment. So the light is being steered by these mirrors onto the slits here. And there's two slits in this slide, and that produces the Young slits interference pattern, which we see on the camera.
The interference pattern is the set of faint vertical stripes at the center of the red spot. These only appear when two slits are open.
One slit, two slits. One slit. Two slits.
With two slits open, the single beam of light is split into two beams which overlap like ripples on a pond. In some places, the ripples reinforce each other, while in others they cancel each other out, creating the pattern of stripes on the screen. But what happens if the intensity of the beam is reduced by a filter so that only one photon at a time can reach the slits?
Now, you can't see the beam at the moment, but if I introduce some liquid nitrogen, we should be able to pick that up. So now you can see the beam scattered by the nitrogen, but you see nothing after the filter. The filter essentially stops everything we can see. The camera can pick up the few photons that are arriving.
The photons arrive at the slits one at a time, so those that get through and reach the screen on the other side should form just two bright lines. They shouldn't interfere and produce the full pattern of stripes, but they do. And this is how the stripes appear on a computer screen.
When one does the experiment with individual photons, the pattern that builds up after one has passed many photons through the apparatus is exactly the same as it was in strong light.
And that's something we just don't understand.
As an undergraduate, we were told, oh, this is because the photon behaves partly as a particle and partly as a wave. Now, that just doesn't make sense. It's gibberish. It's saying that the photon is both in one place and spread out at the same time.
Deutsch believes that the single photons are producing the full pattern of stripes by interacting with other photons that we can't see.
The photon that we can't see is a photon in a parallel universe, a nearby parallel universe, which is interacting with the photon in our universe and causing it to change its direction. The result of the single photon interference experiment is the strangest thing I know. It is conclusive evidence that reality does not consist of just a single universe, because that result could not come about unless there were another nearby universe interacting with ours.
If true, this idea has profound implications for time travel.
When one travels back in time, one does not in general reach the same universe that one starts from. One reaches the past of a different universe.
Could this explain why we haven't met any time travelers?
I don't believe it personally, mainly because this idea is not very constructive. There are not many consequences of this idea which we can test in a real experiment.
I think we can't say for certain, but if I had to lay my bets, and I like to lay bets, I would lay my bets on the simpler non-parallel universe resolution.
Another person who likes to lay bets is Stephen Hawking. He and Kip Thorne have been betting on the nature of the universe for years.
This bet here is probably the most famous one. It was a bet I made with Stephen Hawking in 1974 over whether or not Cygnus X1 is actually a black hole. And Hawking, after 16 years of this bet sitting here, finally conceded. Stephen Hawking and I have occasionally discussed making a bet over whether or not the laws of physics permit you to go backward in time. We haven't been able to conclude a bet because almost all the time we're on the same side of the issue. We both think it is probably impossible.
Stephen Hawking has been skeptical of time travel for years, but even he cannot rule it out for sure.
To make time travel possible, one seems to need both general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs very small scales. These two theories are inconsistent with each other as they stand, so we have to find a new theory that combines them.
Cosmic relationships, like the motions of planets, are governed by Einstein's theory of gravity, general relativity. But these laws do not work on the subatomic level, just as the laws of quantum mechanics do not work on the larger scale. So physicists are searching for a way to unite the two in a single theory called quantum gravity. This is the holy grail of modern physics. A unified description of the nature of space and time on all scales.
So I would like to discuss the Big Bang.
Scientists are still in the process of crafting this theory, and whether quantum gravity will permit time travel through a wormhole is unclear. Yet, they can't resist speculating.
When you try to make a time machine out of a wormhole. Having discovered that it is possible, according to general relativity, to take a wormhole with two mouths and turn it into a time machine, my students and I then searched for some way, some mechanism to prevent this from really happening in the real universe. Because we thought it was ludicrous. You shouldn't be able to do that. And we actually found a mechanism that, in fact, we were able to show always intervenes whenever you try to make a time machine. Suppose that I have two wormhole mouths that I'm going to turn into a time machine. Of course, I do it by taking that mouth and sending it off at high speed out into space. It turns around and it comes back, and just as it's on its way back, it suddenly becomes a time machine, and one can travel through it and get back before one started. Right as it's coming back and settling in, just before the moment when it can become a time machine, suddenly, according to calculations we've done, it explodes. Poof. No more wormholes, no more time machine. The question is why? What made that happen?
What seems to happen is that particles can keep coming round again to the same event in spacetime. This makes the energy density very large, which warps spacetime so that travel into the past is no longer possible.
Birth of the universe.
It seems that energy might pile up inside the wormhole until it self-destructs.
You get, in fact,
But when Thorne applied what is known of quantum gravity, the picture changed again.
it appeared to us that just as that mechanism was about to, in fact, make your time machine explode at the moment you're trying to activate it, right at that moment, our calculations would fail because the new laws of physics, the new laws of quantum gravity would take over, and the techniques we had of computing what happens would no longer be any good.
So perhaps quantum gravity might allow the time machine to exist after all. Thorne decided to see what Hawking made of this.
He got rather disturbed because Stephen is a defender of the establishment. And he really believed that this really would be the mechanism to prevent you ever from making a time machine, and said they've not correctly read the tea leaves of what quantum gravity is going to do. Ultimately, after going back and forth with Stephen several times, we converged to an agreement that he was probably right, we were wrong, the explosion probably will destroy the time machine. But we can't be absolutely sure, we won't know absolutely for sure until we have the full laws of quantum gravity in our hands and we can explore just what they say about the endpoint of the explosion.
In the meantime, Hawking remains skeptical of time travel, a belief he puts forward in what he calls the chronology protection conjecture.
The chronology protection conjecture would make the world safe for historians.
The most likely mechanism that would enforce Hawking's conjecture is the explosion of the wormhole. But this is just a conjecture.
It's a kind of informed guess, which may be mistaken. That's what a conjecture is. And the word conjecture in mathematics is often used as a challenge to future generations to try to prove or disprove.
It's not a principle, it's not a theorem, it's a conjecture because we do not yet know for certain that there is a mechanism in nature that will always enforce it.
Well, if you ask me, do time travels really be possible in the future? I must give the positive reply. You see, it will be possible.
I do not see a way to make time travel possible. However, if I heard that somebody else, some other country, was doing this, I think I might plunge into the game.
I myself believe that there will one day be time travel, because when we find that something isn't forbidden by the overarching laws of physics, we usually eventually find a technological way of doing it.
I believe we will know in 10 to 15 years when we have the full laws of quantum gravity in our hands. My best guess, and I would be willing to lay a fairly heavy odds on this on a bet with Hawking, but he won't take the other side. My best guess is that when we have those full laws in our hands, they will say, no, you cannot make a time machine and go backward in time ever. But until we have those full laws, we just have to leave it as a possibility that remains a possibility.
I wouldn't take a bet against the existence of time machines. My opponent might have seen the future and knows the answer.
Einstein showed that space is curved and time is relative. On NOVA's website, do a simple thought experiment and learn to think like the century's greatest scientist.
Next time on NOVA, the case that inspired The Fugitive.